Good day, everyone. Welcome back. We are in the final stretch of Unit 1 of Physics 30. Today we're going to be starting the topic of conservation of momentum in 2 dimensions, and you're going to need a ruler and a protractor for this. As well, for you West Country Outreach students, you can find this lesson on page 27 of your unit handout. We're going to be covering this over 2 days, so this is the first day or the first video of this topic. What we're going to be looking at today is how to draw vector diagrams that describe what's happening in a 2-dimensional collision. And then, based on those vector diagrams that describe the situation involved, we're going to be using those vector diagrams to solve problems. And these problems, again, are problems where you have collisions occurring in 2 dimensions. Well, a couple of lessons ago, you looked at collisions in 1 dimension. And you had to remember that when applying conservation of momentum, which, by the way, simply says total momentum before the collision is equal to total momentum after the collision, and yes, there are conditions under which that has to be applied. It can only be applied in what we call an isolated system, where the total net force acting on all of the objects is 0. But when you apply the law of conservation of momentum, that's a fact. That's all it says. Total momentum before equals total momentum after. It's really quite simple in principle. But you have to remember that momentum is a vector, and somehow you need to take that direction into account when you start talking about adding vectors together to get a total. So the types of collisions that you have been analyzing are collisions in 1 dimension, for example, between 2 railway cars on a straight track as long as they don't jump the track. Another example would be if you can imagine a V-shaped trough with 2 pool balls in the trough, where the balls can only roll back and forth along that track, but they can collide with each other. Another example, and this was included in the previous lessons, was when you have a firearm and you fire a bullet from the firearm, the bullet goes in 1 direction and the firearm has a recoil velocity in the opposite direction. Although that is not strictly speaking a collision, we apply the law of conservation of momentum because a collision is just when objects push off of each other, and that's all that's happening when you fire a bullet. The bullet pushes off of the rifle. How did we take the vector nature of momentum into account if it was 1-dimensional? The answer is we chose 1 direction as positive and the opposite direction as negative. So when you fire that bullet from the rifle, if the bullet is moving north with a particular speed of, say, 400 meters per second, we would say the velocity of the bullet is positive 400 meters per second. And the recoil velocity of the rifle would be negative. Typically, we use north as positive and south as negative, if that's the dimension. If the dimension that we're dealing with is east-west, we typically choose east as positive and west as negative. It's more complicated, obviously, when you have a collision occurring in 2 dimensions. The reason why is that if you have 1-dimensional motion, there are only 2 directions. Left and right, negative and positive, south and north, west and east. 1 dimension by definition has 2 directions. 2-dimensional collisions do not merely involve 2 directions. We can imagine 2-dimensional collisions as being the collisions, well, we don't have to imagine, it's a fact that when you have 2 pool balls collide on a billiard table, they are colliding in 2 dimensions. That is to say, the objects can be moving north, or they can be moving south, or west or east. They can be moving 23 degrees east of south, 59 degrees north of west, but as long as they are moving along a flat 2-dimensional table, and they don't start moving away from the surface of the earth, or the pool balls don't start jumping up away from the tabletop, that's 2-dimensional motion. So what do we do when there's 2 dimensions, which means really an infinite number of directions? What we have to do is think of the law of conservation of momentum as saying the total of the momentum vectors before the collision must be the same as the total of the momentum vectors after the collision. And it will lead us to what we call a vector diagram, and that will lead us to the solution to the problem. When I say the sum of the momentum vectors before is the same as the sum of the momentum vectors after, I'm telling you momentum is conserved. Because the sum of the momentum vectors before is the total momentum before. And the sum of the momentum vectors after is the total momentum after. So it's just, if you like, it's going to be a geometric way of showing momentum before in total equals momentum after in total. Let's take a look at an example here. We're going to learn over the coming days that there are a number of ways to do many of these two-dimensional collision problems. But the first example I want to do involves a right-angle collision where the objects stick together. And there is always only going to be one way to do this type of problem. And it's going to be exemplified by what we do in the note package here. What we have is a 2,000 kilogram car that's moving east at 24 meters per second. It enters an icy intersection and collides with a 3,100 kilogram Jeep moving north at 10 meters per second. And like many collisions, the vehicles become, in this case, coupled together, which means they stick together. They lock together at least momentarily after the collision. And we want to find their common speed and direction of travel after the collision. We're going to use a vector diagram and basic grade 10 and grade 9 and 8 triangle geometry in the form of the Pythagorean theorem. So the first thing we want to do is understand that when we draw these on paper, and you are expected to draw these vector diagrams on paper or interpret them when they're given to you drawn on paper, the first thing we need to know is that the map directions are given by this. When you're looking at a sheet of paper, north is always to the top of the page, south is to the bottom, east is to the right, and west is to the left. So what we have going on here, and this that we're drawing, by the way, is not a vector diagram. It's just showing what's happening, is we have a car moving in one particular direction, to the right, which is east. We have a Jeep moving towards the top of the piece of paper, which is north. And they collide and move off in some particular direction. So this is a picture or a diagram showing what's happening before and after put together into one diagram. I know you know this, but I will say it anyway. When you look at this page right now, you see two blue cars and two black vehicles. There's only one blue car and only one black vehicle. It's a before and after. This is not a vector diagram. What I would like you to do is take a minute, please, and use the formula for the magnitude of momentum and calculate the magnitude of the momentum of the car. You're given its velocity and you're given its mass, so you can take the speed times the mass. Do the same thing with the Jeep. Pause the video, and as soon as you have those numbers, start the video again. So I'm getting 48,000 units of momentum, and you've learned that momentum can be expressed as the product of newtons times seconds. I'm getting 48,000 newton seconds for the cars, magnitude of momentum, and 31,000 for the Jeeps. If you didn't get those numbers, pause the video again and double check your calculations. All you were doing is taking the mass times the speed for both. I want you to notice, and this is something you would probably discover on your own, that the amount of momentum in the east direction that the car has is greater than the amount of momentum in the north direction that the Jeep has, which is why if you look at the arrow that I've drawn for the direction they collectively move off at, it's more east than north. So that's the first step. This is not a vector diagram, but what we want to do with it is turn it into a vector diagram. What I've got drawn here, and just hold off on drawing it and instead listen to what I'm telling you, is that Those two bluish vectors are each momentum before the collision. The 48,000 Newton seconds is the momentum before the collision, east of the car, and the 31,000 Newton seconds north is the momentum of the Jeep. The total momentum before is represented by what I get when I draw the two vectors before tip to tail. When you add vectors together that are not in the same direction or in opposite directions, we have this general rule. It goes all the way back to physics 20. You don't figure it out in your head. You don't add or subtract the numbers. What you have to do is draw that diagram. Draw the two vectors tip to tail. So the two blue vectors are the total momentum before. But the total momentum before has to be equal to the total momentum after. And the total momentum of those blue vectors is a single vector from where you started drawing it to where you finished drawing it. This is basic vector algebra from physics 20. You may have been dealing in physics 20 with velocities or displacements and not momentum, but you have seen this calculation in a previous lesson. We've done this before. It's just now we're adding two momentum together that means something. They have to do with a collision. So in order to find the magnitude of the momentum, you need to use the Pythagorean theorem. In order to find the direction of the momentum, you're going to have to use trigonometry. And specifically, you can use hypotenuse squared equals other squared plus other squared to find the hypotenuse. And you can use tangent of theta equals opposite over adjacent to find theta. Make sure your calculator is in degrees. You can go ahead and pause the video when you've got those results for the momentum magnitude and the direction. You can start the video again. All I'm doing is taking 31,000 squared plus 48,000 squared, then taking the square root. For theta, I'm just taking the inverse tangent of 31,000 over 48,000. And again, I don't mean to trivialize the calculations, but these are calculations that are grade 10 and earlier calculations. We still haven't answered the question. What we know is that the car and Jeep together have this momentum in that direction after the collision, immediately after the collision. If we want to find the speed, we have to divide the magnitude of the momentum by the mass, because momentum is mass times velocity. So when you take the 57,140 Newton seconds and divide by the mass of both vehicles together, the total mass after the collision is 5,100 kilograms. You need to, in the final stage, when you talk about that object's momentum after the collision, understand that it is not a car and a Jeep. It's a car and a Jeep together. It's not two separate vehicles, it's one vehicle. And of course, the direction of that velocity of 11 meters per second is 33 degrees north of east. So that's the first example today. We're going to look at one more example. I would recommend, particularly for you West Country Outreach students, that if you did not get this answer, just pause it here before you go on to the next example with me. Rewind the video if you need to, find your mistake, get it figured out. All of the remaining examples are quite complicated. And most of the time, any of these remaining types of examples can be done in multiple ways. We're only going to be looking at doing it one way today, and it's going to be with a scale diagram. This is what we refer to as a glancing collision. If you've ever played pool, and I think most people have, if you've ever had a chance to play pool, very rarely is it the case that you're going to hit the target ball with the cue ball dead on. Most of the time you hit the target ball a little bit off center with the cue ball because you don't want the target ball to go straight. You want it to go in a different direction. So that's what we refer to as a glancing collision. What do we have here? A steel ball of mass 500 grams is moving east at 2 meters per second. It hits and glances off of a 300-gram steel ball that's initially at rest. Now, I've probably exaggerated the size of these, but the larger ball is the 500 gram one and the smaller is 300 grams. The first ball moves off at 1.5 meters per second at a particular angle, and we're asked to determine the velocity of the other ball. So the 500 gram ball moves off at an angle of 35 degrees south of east. So we're going to be using a scale vector diagram, and my recommendation is this is a good method for multiple choice questions only. I will tell you right now that when you solve this problem in a more mathematical way, using geometry and trigonometry, it's a lot of work. It can be quite involved, and for some students it can be a little overwhelming. So if you have a multiple choice question that is like this, if you know what you're doing with a vector diagram, a scale vector diagram, you can get the answer very, very quickly. And that's what we're going to do. This is where the ruler and the protractor comes in. First thing is, we've got a 500 gram ball moving at 2 meters per second. If we take the mass of that ball, which is 0.5 kilograms, times the speed of 2 meters per second, we know what that momentum is. The momentum of the first ball before the collision is 1 Newton second. We're going to need to know the magnitude of the momentum because this is all about conservation of momentum. As well, after the collision, we have that 500 gram ball, which is 0.5 kilograms, multiplied by the speed of 1.5. So if you take your calculator and take 0.5 kilograms times 1.5, you get 0.75 Newton seconds for the 500 gram ball after the collision. We need to know those numbers. And as always, for you people following along in a note package, if you're at West Country Outreach or otherwise, pause the video when you need to. So here is a pair of diagrams showing what's happening before the collision and what's happening after the collision, immediately after the collision. Before the collision, the one steel ball of 500 grams is moving to the right with 1 Newton second of momentum. After the collision, it is glanced off of the smaller ball and the 500 gram ball is moving 35 degrees south of east with a magnitude of momentum of 0.75 Newton seconds. If we put them together, this is kind of a before and after snapshot in time combined. And again, this is not a vector diagram, but it is something that you should understand how to draw. What we're trying to find are those two question marks. So that's what we're looking at, a before and after. This, however, is a vector diagram. In this particular collision, those two brown vectors on the left, these two vectors that I'm going to highlight for you, are both representative of vectors after the collision. So we know that when we draw those two vectors tip to tail, we get something which has to be equal to the total momentum after. But the total momentum after has to be equal to the total momentum before. So on the right-hand side, this is a vector diagram now. On the right-hand side, I've drawn my two momentum vectors afterwards, tip to tail, and the total of them is represented by that green line, a single vector from where I started drawing to where I finished drawing. That's the total momentum after, but it has to be equal to 1 Newton second. So this is the vector diagram that we are dealing with. And we're going to draw that vector diagram with a ruler and a protractor as accurately as we can. I mean, you don't need to break out the AutoCAD or a drafting table or anything, but we want to be fairly accurate. So we have to draw this diagram on the right using a scale of some kind. Well, I might recommend the following scale. And it's entirely up to you. I might recommend that for every 1 Newton second on the physics diagram, we draw a line that's 10 centimeters long. Could you do this with a scale diagram where 1 Newton second is drawn as 1 centimeter? You could, but your diagram would be so small, it would just cause a lot of problems. So now that we've chosen that scale of 1 Newton second equals 10 centimeters, we can go ahead and we can draw with our ruler a line with an arrowhead on the end of it pointing to the right that is 10 centimeters long. Again, it doesn't have to be perfect, but I think there's some acceptable level of accuracy that's expected here. Now what we need to do, let's go back and look at that vector diagram, is we have to draw that 0.75 Newton seconds 35 degrees below the left side of that green vector, pointing in that direction of 35 degrees below, and it has to be drawn so it's 0.75 Newton seconds. Well, since we're dealing with this scale, I've chosen a fairly simple scale to work with here. Since we're dealing with that scale, 1 Newton second was 10 centimeters. 0.75 Newton seconds will be 7.5 centimeters. You can choose whatever scale you like. You can set up ratios to find the lengths that you need to draw, but this one is fairly straightforward, that if you take the number of Newton seconds and times 10, you get the length that it's going to be drawn. So now what you need to do is take your ruler, just put it out of the way for a second here, take your protractor, turn it around and put it on here at the start, and draw a line that is 35 degrees below that green vector. Now, I would recommend to you, to begin with, and obviously how you do this is a little bit different than how I do it. I would put a ruler down. I say that because I have virtual tools here. Put a ruler down and angle it so that it's at 35 degrees and draw a fairly long line. Maybe even longer than that, and you'll see why in just a second. The reason for that is, in order for you to actually draw the vector of 7.5 centimeters, you need to use a ruler. So you have to get rid of your protractor, put your ruler up here, Now I'm kind of cheating a bit because if you look on the left-hand side of the page, it tells me that's 35 degrees, so my angle wasn't drawn perfectly. It's about there, but I want to draw this at 7.5, and I almost hit it bang on. I want 7.5 centimeters, so I'll just put a mark here. That's going to be where my arrowhead ends. So this is one of the vector momentums afterwards. We can start putting some labels on some of this. This is 1 Newton second. This is 0.75 Newton seconds. This angle is 35 degrees, although we don't really need it anymore. And that means that the other vector, in order to give us the proper sum, has to start here and end here. It's not perfect. I would say to you that you're probably going to get a better diagram with more accuracy using a pencil that's sharpened properly and a sheet of paper than I will up here with these thick lines. So how do we get the answer to the question? Well, let's label this other vector. This is the momentum afterwards of the 300-gram ball. Well, how do we determine that? What we do is we measure it. Take our ruler and we measure how long that is. And it's looking like 5.65 centimeters, roughly. which translates to 0.565 Newton seconds. Remember that the length in centimeters is 10 times greater than the actual magnitude of the momentum. Now we also need to determine the direction. And the direction that this brown vector is pointing, let me highlight the vector for you. The direction that this is pointing needs to be described starting an angle drawn at where the vector starts. So we need to measure this angle here. Now the difficulty for you is that you have to draw that dotted line nice and horizontal. It has to be drawn parallel with that green line at the top. With me, that's not an issue because this line kind of locks into place as soon as I get it to be horizontal. So you're going to have to do a bit of eyeballing here. I need to measure that angle. So you're going to put your protractor down. Whoops. And as accurately as you can, measure that angle. And I'm getting, it's a little bit closer to 50 than 49 degrees, so I'm going to say it's 50 degrees north of east. Just jot this down, 50 degrees north of east. So we are almost done. The only thing we have to do is remember that this magnitude of the momentum of 0.565 Newton seconds is equal to the mass times the magnitude of the velocity so we're going to have to divide that by the mass. So the magnitude of the velocity is going to be found by taking that 0.565 Newton seconds and divide by 0.3 kilograms. Let's see what we get here. 0.565 divided by 0.3. So I'm getting 1.88 meters per second at an angle of 50 degrees north of east. When you compare what we got using a scaled diagram, and I hope that you got very, very close to the same numbers, to the actual answer that you would get, and we're going to redo this same problem tomorrow using formulas and geometry and trigonometry, it's 1.9 meters per second, which is bang on with what we got, because if we round our answer to 2 digits, we'll get 1.9. The angle is at 49 degrees north of east. That is so close as to not even worry about the difference. This is a quote from a document from Alberta Ed, A1.3S, which is just a part of the curriculum. It's a code for teachers. Deals with two-dimensional analysis. For diploma questions, and for my exam questions as well, a well-drawn, scaled vector diagram will give you results good enough to get the marks on the exam. You can, however, use what's called rectilinear components, or you can use the sine or the cosine law, but sometimes they are more time-intensive and sometimes difficult for some students. So for some students, you will want to use a scaled diagram because that's maybe your best bet at getting the answer right. These are the problems that I recommend going with this part of this topic. Questions 1, 2, and 4 on these pages of your handout deal with what we were just doing, and questions 6, 7, and 8 are right angle collisions where you use the Pythagorean theorem and the tangent ratio to solve the problem. In the next lesson, what we're going to do is look at the more mathematical approaches, the trigonometric approaches, the mathematical approaches that rely on geometry rather than drafting. So I hope that was helpful. We'll see you all soon. Take care.